Each video module consists of a video program presenting an overview of the topic and a manual containing much more detailed information as well as exercises. To master each topic, you must use the module's components together. View the video program, read the manual, and work the exercises. Porosity and permeability, the properties that give a rock the capability to be a petroleum reservoir. These properties, for the most part, are controlled by the environment in which the rock was deposited. Thus, predicting where porosity and permeability are present in the subsurface depends on the analysis and identification of sedimentary facies.
In the first part of this module, we will look at the basic concepts of depositional environments and facies. We'll then examine important environmental indicators preserved in the rock record, concentrating mostly on clastic facies. In the second part of the module, we'll examine the techniques and tools used to diagnose environments of deposition. Finally, we'll take a brief look at carbonate facies. Coverage of each reservoir facies is reserved for the pertinent modules of this GL 500 series. Now let's see what facies analysis is all about.
The essence of facies analysis is the construction of a geologic model, one that describes an ancient sedimentary environment, like this delta model. Of course, we can only look to modern equivalents as analogs to the construction of these models. But in doing this, we must apply caution, because the factors that control these processes, like climate, tides, and vegetation, were most likely much different in the geologic past than they are today. We are concerned naturally with only depositional sedimentary environments, sites where sediment is deposited and preserved as sedimentary rock. Major sandstone depositional environments in non-marine settings that produce rocks of reservoir quality range from alluvial fans that pass transitionally into braided streams that with decreased gradient pass into meandering streams. Reservoir quality sands may also be formed as dune deposits in aeolian environments, as well as in lake environments. Important coastal settings include deltas and barrier islands. In offshore marine settings, good quality reservoir rock may be deposited as sand ridges on the continental shelf and as channel sands and lobes in deep-water submarine fans. Most carbonate rocks in the geologic record were apparently deposited in settings related to carbonate shelves with the coastal, shelf margin, and foreslope settings of these shelves providing the most favorable sites for the deposition of reservoir rock. The stratigraphic analog of a major depositional sedimentary environment is a three-dimensional mass of rock termed a depositional system. A number of these depositional systems may be joined together to form a systems tract. Here we see a typical systems tract composed of fluvial, deltaic, and marine shelf systems. These depositional systems are composed of units of rock called lithofacies. A lithofacies, often called sedimentary facies or simply facies, is a three-dimensional mass of sedimentary rock that may be distinguished from adjacent rocks on the basis of its lithology, texture, geometry, sedimentary structures, and paleontology. Lithofacies are formed in response to depositional processes inherent within a specific depositional environment or sub-environment. An active depositional system like this deltaic system is made up of a number of sub-environments, each producing a characteristic lithofacies. Lateral and vertical contact between facies may be sharp, like between this distributary channel and underlying shale, or they may be gradational, as between this distributary mouthbar sand and pro-delta shale.
Now let's look at lithofacies in the context of the physical relationships of the strata themselves.
This is accomplished by looking at sedimentary units termed depositional sequences, that is, stratigraphic units of rock composed of a relatively conformable succession of strata that are bounded by unconformities, or their correlative conformities. All of the rocks within a depositional sequence are genetically related and deposited within a given period of geologic time. Sequences are composed of a number of bedding surfaces that correspond to timelines. Formations, or lithofacies, may parallel these chronostratigraphic bedding surfaces, or, as shown here, they may cross the bedding surfaces, in which case they are said to be time transgressive. A portion of the upper and lower boundaries of sequences should display some discordance. Upper boundary discordance may result from erosional truncation, or by toplap. Lower boundary discordances result from an unconformity, or from baselap, which is of two types, onlap and downlap. Toplap occurs mainly where non-deposition takes place at the top of inclined strata, such as in this example, where base equilibrium conditions on a delta plane directly overlie delta front foreset beds. Onlap occurs where strata terminate up-dip against an inclined surface. For example, on the flank of a basin that is being progressively infilled with sediment. Downlap occurs where inclined strata terminate against a relatively horizontal surface. That is, where sediment starvation takes place, at the distal end of a prograding delta or submarine fan.
Let's now consider how facies relate to chronostratigraphic bedding planes. To illustrate this relationship, we'll see how the buildup of coastal sediments during a relative rise in sea level can vary, depending upon the amount of sediment influx.
In the case of relatively low sediment influx, transgression takes place and facies climb shoreward through time, with deeper water facies overlying shallower water facies. When sediment influx is high, regression takes place, and facies climb seaward through time. In this case, shallower water deposits overlie deeper water facies. When sediment influx and sea level are in balance, facies may climb vertically across chronostratigraphic bedding surfaces. Note that in all cases of relative sea level rise, stratal surfaces display coastal onlap. A relative still sand of sea level results in coastal deposits not being able to aggrade vertically. Only horizontal progradation takes place, in this case producing a toplap relationship of stratal surfaces. Let's look again at this fundamental relationship between transgressive and regressive sequences, using a barrier island system as a model. In the case of transgressive shorelines, deeper water sediments overlie shallow water and continental sediments, and facies climb landward through time. In regressive situations, continental and shallow water sediments overlie deeper water sediments, and facies climb seaward through time. Just how do we identify a sedimentary facies and thus determine the environment of deposition? The 5 basic parameters that define a facies are its lithology, sedimentary structures, paleontology, geometry, and associated environments.
Let's examine each of the 5 basic facies parameters, starting with lithology, one of the most important, yet also one of the easiest facies parameters to observe.
Lithology is one of the best indicators of depositional environment. This is particularly true of carbonates. Most carbonates are biogenic in origin and are produced either in situ or, at most, within a few kilometers of deposition. Therefore, the shapes, sizes, and sorting of carbonate sedimentary grains bear a strong relation to the physical processes that characterize a particular depositional environment. On the other hand, the lithology of terrigenous clastic sediment, in addition to being dependent on depositional environment, is also controlled by the type of rock from which it was derived and its transportation history. The depositional fabric of terrigenous rocks like sandstones, however, is easier to detect than that of carbonates. This is so because terrigenous sediments are generally much less susceptible to post-depositional diagenetic changes than carbonates.
Because of these inherent differences in depositional and diagenetic history, we shall examine the lithology of terrigenous and carbonate sediments separately, saving the entire subject of carbonates for the latter part of this module. Let's now look at the first of our diagnostic criteria, lithology.
Aspects of lithology important to the analysis of subsurface facies include grain size, as well as chemistry and mineralogy. The grain size of a terrigenous clastic sediment depends primarily on the energy of the depositing current. Generally, environments with higher energy currents produce coarser-grained sediments, and lower-energy environments produce finer-grained sediments. Grain size tends to decrease in the direction of transportation, and sorting increases along with the length of time the current is active. Sedimentary facies commonly display characteristic vertical profiles in which grain size finds upward, coarsens upward, or remains constant. The determination of such vertical variations in grain size can be extremely valuable in the diagnosis of a depositional environment. Channel sequences form by lateral accretion and, regardless of depositional environment, always display to some degree profiles that fine upward, generally from a scour base. On the other hand, bar-type sands almost always display coarsening upward profiles, often capped by an abrupt facies change to fine-grained material. Examples of this latter type include regressive barrier island sands, shallow marine bars, delta front bars, and even aeolian dunes. Facies displaying blocky profiles whereby grain size remains relatively constant include some braided stream deposits and tidal sands. Often, sands originating in different sub-environments will coalesce to form a single vertical grain size profile. One example is a deltaic distributary channel sand that, as it builds outward, incisors down into an underlying delta front bar sand, forming a deltaic couplet.
Remember that no single environment has a unique grain size profile, and similar profiles may be produced by different environments. Therefore, profiles should be interpreted along with as much supplementary data as possible. Now let's turn our attention to another aspect of lithology, the chemistry and mineralogy of sediments. These parameters are governed mainly by minerals precipitated at the time of deposition, thus providing important clues to the diagnosis of the environment.
The oxidation reduction potential, or EH, of a depositional environment may be revealed by the type of iron minerals present. For example, reddish ferric oxide cement is formed in an aerated oxidizing environment. Thus, red, orange, or brown sediments indicate continental deposition, like in this alluvial fan, or this braided stream. These settings are usually above the water table, where acidic, oxygen-rich groundwaters are able to percolate through the sediment, precipitating red ferric iron oxides and destroying organic matter. Drab-colored sediments, green or gray in color from ferrous oxide, and often with preserved organic matter, are formed in a reducing oxygen-deficient environment. They usually indicate deposition below the groundwater table, for example in meandering floodplains, coastal environments, and marine settings. The presence of abundant pyrite and preserved organic matter generally indicates extreme anaerobic conditions that can take place in marine or lacustrine basins, where circulation of oxygen-rich water is restricted.
Using color as a rule of thumb, however, must be done with caution. Some deep marine sediments are red. Also, secondary reddening often takes place under unconformities. And red beds may become gray-green if they are flushed by strongly reducing connate fluids.
Information on depositional environment may be provided by the occurrence of certain common minerals. For example, the sandstone we see here contains glauconite, a greenish-colored complex hydrous aluminosilicate. This orthogenic mineral seems to form only in marine sediments on the continental shelf. It is quite unstable and generally is unable to withstand significant reworking. Its presence, therefore, has been used with some success as a reliable indicator of deposition in a marine environment, but its absence does not necessarily indicate a non-marine environment. Another mineral that can be helpful in environmental diagnosis is detrital mica. Flakes of mica tend to be winnowed out of high-energy environments, like this, by turbulence and strong currents, and then carried away to be deposited in lower-energy environments. Micaceous sands, therefore, tend to be absent from well-winnowed environments, such as barrier islands, shallow shelf bars, and aeolian dunes. Particles of carbonaceous material like lignite and coal are a common minor component of many sands. Because this material is derived mostly from land plants, it is commonly found in fluvial, lacustrine, and deltaic sands. But its presence does not necessarily indicate a non-marine environment. Carbonaceous material can be found in marine deposits as well. Coal is quite stable and can survive transport into deep marine environments, like submarine fan systems. Carbonaceous debris is easily winnowed away, and, like mica, its absence is a valuable index of winnowing. Shell fragments are another common constituent of sands. Some of this shelly material may come from freshwater organisms, but calcareous shell particles often are not preserved in continental sediments because of leaching by acidic meteoric waters. Shell material, therefore, most likely indicates a marine depositional setting. Let's see how the presence or absence of these four materials, glauconite, mica, carbonaceous material, and shell debris, can be used to define four major groups of sandstones. First, sandstones deposited in high-energy marine environments, like barrier islands, bars, and shoals, may contain glauconite and or shelly sands, but be without carbonaceous detritus and mica. Deltaic fluvial and lacustrine sand may contain carbonaceous and or micaceous material, but being non-marine, would not be expected to contain glauconite or shell debris. Deep-sea sands can contain all four constituents: glauconite, mica, carbonaceous material, and shell debris. Aeolian sand should be barren of all four materials.
There have been many attempts to use clay minerals as indicators of depositional environments. These attempts, however, have met with little success, primarily because the chemistry of clays reflects parent rock mineralogy, weathering, climate, and diagenetic history, as well as depositional conditions. There does, however, seem to be a broad relationship of illite and montmorillonite to ancient marine rocks and kaolinite to continental rocks. Now, what about trace elements?
Studies have shown that continental sediments that have undergone long periods of subaerial weathering typically contain the trace elements titanium and thorium. Marine sediments, on the other hand, are more enriched than continental sediments in the trace elements boron, chromium, copper, gallium, nickel, and vanadium, with vanadium being concentrated in highly anaerobic facies.
Having looked at lithology, let's now consider another facies parameter: sedimentary structures.
Primary sedimentary structures are formed at the time of deposition, or shortly thereafter, and prior to consolidation. There is a great variety of these primary structures that include various kinds of surface markings, bed forms, bedding plane stratification, and deformation structures. Evidence for these structures is seldom found in well cuttings, having been destroyed by the drill bit. There are, however, some structures that may be detected in cores, or sometimes indirectly by the dip meter. Important among these are current-generated stratification features produced by various sediment bed forms. Here we see how the several basic bed forms develop in response to sediment size and flow velocity. Small ripples are downstream migrating bed forms, produced by relatively low current velocities in sediment ranging from silt to medium-grained sand. Small ripples are less than several centimeters in height and have gentle up-current and steeper down-current slopes. The type of stratification produced by this bed form is called ripple cross-lamination. It occurs as thin sets of concave upward foreset laminae, dipping in the direction of the current flow. Each set tends to be flat, elongated, and tongue-shaped, with thicknesses generally less than a few centimeters. With increased sediment size and current flow, large ripples are developed. These are of two types: two-dimensional and three-dimensional. Two-dimensional large ripples are straight-crested features, commonly with superimposed small ripples that vary significantly in height from 10 centimeters or so up to a few tens of meters. The smaller versions are called megaripples, and the very large forms, sand waves. Two-dimensional large ripples produce a type of stratification called large-scale tabular cross-stratification. Sets are planar and parallel to each other and vary in thickness from a few centimeters to up to 10 meters or more. The four-set laminae are generally planar and commonly dip 30 degrees or more. With increased current velocity, two-dimensional ripples pass gradationally into three-dimensional forms. Three-dimensional large ripples have uneven crests and troughs and range in height from about 10 centimeters up to a few meters, being smaller on average than two-dimensional ripples. They produce a type of stratification called trough cross-stratification, which may occur in sediment ranging from fine sand to very coarse sand. When viewed in a section parallel to flow, sets are approximately parallel, with occasional wedging out, and thus can be mistaken for a tabular type of cross-stratification. But when viewed transverse to flow, a distinctive trough pattern, sometimes called festoon, is clearly discernible. Plain beds are flat beds that are developed at still higher flow velocities in all sizes of sediment. They also form in a narrow range of low velocities, but only in coarse sediment. Plain beds, as one might expect, produce a type of stratification called planar lamination. Other types of current-generated stratification include oscillation ripple cross-lamination, which is produced by the back-and-forth action of waves. Hummocky cross-stratification is a type of large-scale cross-stratification produced by oscillating flow mainly in coarse silt and fine sand. It is believed to form on marine shelves and on the lower shore face from the action of large storm waves.
The third important parameter of sedimentary facies is paleontology. Now, this is a specialized science usually beyond the ordinary petroleum geologist. However, it's worth taking a brief look at the role of fossils in environmental reconstruction.
Microfossils are by far the most abundant of all fossils in the paleontological record. Also, they generally survive the action of the drill bit, and quantities of them are retrieved from well cuttings, while macrofossils become fragmented and generally unidentifiable by drilling operations. Microfossils are most often found in the cuttings of fine-grained sediments like shales and limestones, and are relatively rare in sandstone.
A major application of microfossils is in biostratigraphy, that is, in their use as chronometers of geologic time. In this module, however, we are concerned with the use of fossil remains as indicators of sedimentary environments.
Foraminifera and ostracods are the two most important varieties of microfossils employed in environmental analysis. This is because some suborders and genera of foraminifera and ostracods are benthic. That is, they are bottom dwellers and live only in specific environments related to depth and salinity. Thus, when found as an assemblage of fossils in the same place they lived, they can provide a direct indicator of depositional setting. Foraminifera are the most widely used microfossils. They are single-celled organisms that come in a wide variety of shapes. They have existed since the Ordovician, with 20,000 species having been classified, 4,500 of which are still in existence. Foraminifera, both planktonic and benthic forms, inhabit a wide variety of aquatic environments, from very shallow water to depths of 5,000 meters, and in water ranging from brackish to hypersaline. They are not, however, found in freshwater lakes.
The habitat of foraminifera depends to a great degree on the composition of their skeletons, or tests. Now, three basic groups of test composition are recognized.
Agglutinated tests are formed from material borrowed from the habitat, like grains of quartz, flakes of mica, clay material, and various skeletal debris. Porcelaneous tests are opaque, calcareous ones that appear white and brilliant in reflected light. Hyaline tests are calcareous skeletons characterized by their glass-like transparency.
Let's see how these various groups of foraminifera relate to environment. First of all, salinity.
Most benthic foraminifera inhabit waters of a normal salinity. However, certain groups having porcelaneous tests can live equally well in hypersaline lagoonal environments. Other types, such as certain agglutinates and hyalines, prefer brackish lagoons and estuaries. Some foraminifera may be found in all environments. Here we see the depth distribution of recent benthic foraminifera. Generally, benthic foraminifera with porcelaneous tests live in shallow waters, while hyaline tests occur everywhere but in deepest waters. Agglutinated types similarly occur everywhere, but they also survive at great depths, up to 5,000 meters. In addition to foraminifera, ostracods also provide important information on depositional environment. They are the most advanced form of microfossils used, being crustaceans like shrimp within a bean-shaped calcitic shell. Ostracods have existed since the Cambrian and inhabit every aquatic environment, both marine and freshwater. Many varieties are benthic and prefer quiet, still waters where fine-grained sediments are rich in organic material. Basically, 3 broad assemblages of ostracods are recognized based on sensitivity to salinity. These are freshwater, generally with thin, smooth shells; brackish water, with various shell markings depending on salinity; and marine, with robust, often ornamented shells. Marine benthic varieties can also be used to give marine water depth. For example, certain assemblages indicate shelf, bathyl, and abyssal depths. Other common microfossils, some of which have value as environmental indicators, include calcareous nanofossils, radiolarians, diatoms, conodonts, spores and pollens, and dinoflagellates. Information on these can be found in your manual.
The fourth important parameter of our lithofacies is its overall shape or geometry. Geometry is controlled by many variables. For example, topography of the original depositional surface, climate, paleoslope, nature and amount of sediment supply, and intensity and direction of local depositional currents. Let's look at the basic shapes of some major sandstone facies.
Here we see the elongate bar shape of a barrier island or shelf ridge sand, typically with an abrupt concave downward top and a gradational base. Channels are straight to sinuous or lobate, but all generally have abrupt concave upward bases that cut into underlying sediment. Their tops are gradational. But remember that channels may be formed in several different environments, for example, alluvial, deltaic, tidal flat, or deep marine. Here we see the distinctive shape of an alluvial or submarine fan, with its concave downward upper surface when viewed along a strike section. Also, more than one shape can be produced by a single environment. For example, deltaic river mouth bars may assume a variety of shapes, depending on the relative intensities of fluvial versus marine processes. We can, however, make some generalizations regarding facies geometry. Fluvial channel facies tend to be elongate to sinuous sand bodies, trending essentially perpendicular to the paleo shoreline. Barrier island and shelf ridge sand systems develop as elongate shoestring bodies parallel or slightly oblique to the paleo shoreline. A sheet or blanket geometry is generally of little environmental significance. Detailed study may reveal, however, that a sand sheet is actually made up of a series of coalesced braided stream channels, barrier island shoestring deposits, or Aeolian dune sand bodies. Traditionally, geometry has been the last aspect of a subsurface facies delineated. This was because data from a number of boreholes were required to adequately define the lateral and vertical extent of a body of sedimentary rock. But with the advent of modern seismic techniques, such as 3D seismic and color-coded displays, the geometry of a subsurface facies, in some cases, can be reliably determined in the early stages of exploration.
The final facies parameter that we will discuss is the nature of associated facies. Now, often the identification of certain ancient environments or sub-environments is difficult. Either the environment does not inherently possess enough diagnostic characteristics, or we may not be able to obtain sufficient data for positive identification. The analysis and identification of associated environments, then, becomes an important tool in the interpretation of the facies at hand.
With the rise and fall of sea level, shorelines transgress landward or regress in a seaward direction. Environments migrate laterally over one another, resulting in the deposition of a conformable succession of genetically related sediments with gradational facies transitions that are both systematic and predictable. These gradations take place in both lateral and vertical directions. Similar gradations develop between the subfacies of a depositional system as subenvironments shift spatially with time.
Now that we have some idea of what to look for in the way of environmental indicators, how do we go about obtaining this information? As mentioned earlier, the analysis of any sedimentary environment depends on two basic types of information. One is derived from direct observation of the rocks themselves, from outcrops, cores, and well cuttings. The second type is indirect, generated by instrumentation, wireline logs and seismic surveys.
The most valuable direct information is, of course, derived from outcrops, particularly data on large-scale sedimentary structures that are otherwise generally unobtainable. The petroleum geologist, however, is primarily concerned with the subsurface. Key stratigraphic horizons may not be exposed at the surface. Even if exposed, facies changes may result in the outcrop information being of little value for the problem at hand. Let's look at another direct source of information, one that is usually readily available to the subsurface geologist: cores and drill cuttings. Most rotary drilling bits provide cuttings large enough and fresh enough in appearance to allow lithological evaluation. It is possible, therefore, while drilling is taking place, to prepare an accurate lithological section of a well, called a sample log. There are several methods for preparing a geological sample log. The most important of these, for facies analysis, is a log that provides a complete written description of each sample. Important formation boundaries should be noted, and a symbolic lithological column useful for quick reference included. It should be emphasized that the resulting log is only as reliable as the experience and qualifications of the person preparing it. Cores provide the other source of direct data from boreholes. Bottom hole conventional coring is done during drilling, and sidewall coring is accomplished after drilling. Conventional cores provide excellent lithological and paleontological samples, often continuous and undisturbed. Sedimentary structures are frequently visible, and valuable information on the nature and direction of paleocurrents can be obtained, particularly if the position of the core with respect to magnetic north is recorded. Coring equipment is, however, expensive, and coring proceeds at slow rates, thus adding to rig time costs. Therefore, a geologist or engineer must provide strong justification when recommending a conventional coring operation to management. Sidewall coring is carried out after drilling is completed by means of a core gun on a wireline logging cable. At the appropriate sample depth, a 1-inch hollow bullet is fired horizontally into the borehole wall, and a core up to 2 inches long recovered. This type of core is small, but relatively cheap, and can be obtained selectively over an extensive depth range in the well bore. Although often damaged by impact, sidewall cores can provide useful data on lithology and paleontology for environmental analysis.
Let's now turn our attention to indirect sources of information that are provided by wireline logs and seismic. Wireline logs provide two basic functions for the geologist. First, they provide data for evaluating the hydrocarbon-bearing properties of a zone, called formation evaluation, and secondly, they provide control for subsurface mapping.
In formation evaluation, logs are used to define physical rock characteristics, such as lithology, porosity and permeability, to distinguish between gas, oil, and water in the reservoir, and to estimate reserves. In subsurface mapping, logs are used to correlate zones, to construct cross-sections, and provide control for structure and isopac maps.
But what about the use of logs in facies analysis? First of all, the spontaneous potential log and gamma ray log can serve as indicators of vertical grain size variations. Secondly, certain types of sedimentary structures can be interpreted from the dip meter log. Let's look at how vertical grain size profiles can be revealed by well logs.
The SP log responds to the permeability of a formation. A major reason for the reduction of permeability is the presence of shale. The SP log thus reflects shale content. Because the amount of shale matrix in most sandstones tends to increase with decreasing grain size, the SP log can be used as an indicator of vertical grain size variations. The SP curve, measured in millivolts, varies between two extremes: a shale baseline and a line corresponding essentially to clean sand. With increasing grain size, the curve tends to deflect to the left toward the clean sand line. These relationships hold true only for relatively thick beds with formation water resistivities less than the drilling mud. For example, saline formation water and freshwater drilling mud. Formation waters that are more resistive than the drilling mud, for example, fresh formation waters, will cause a reversal of SP deflection to the right side of the shale baseline. Also, the SP will not work in oil-based muds because they are non-conductive. Use of the SP log as a reflection of vertical grain size changes is valid only for sediments with primary intergranular porosity. Thus, it is generally not a reliable indicator of vertical grain size distribution in cemented sandstones or in carbonates that have undergone significant diagenesis. The second wireline log used to obtain vertical grain size profiles is the gamma ray, which measures the natural radioactivity of formations. Shale-free sandstones and carbonates usually have low concentrations of radioactive materials, while shale is relatively rich in the radioactive elements uranium, potassium, and thorium. The gamma ray log thus indicates the amount of shale in a formation. As mentioned previously, the amount of shale tends to increase with decreasing grain size. Therefore, as in the case of the SP curve, deflections of the gamma curve to the right indicate decreasing grain size. The gamma ray log, like the SP log, has its limitations though. Clean, shale-free sandstone may produce a high gamma ray reading if it contains potassium feldspars, micas, glauconite, or uranium salts. The high readings produced in such cases can make a clean sand appear fine and shaly.
We've seen that no single environment displays a unique grain size profile. Thus, SP gamma ray curves should take into account as much supplemental data as possible. Let's look at the environmental interpretations of 4 basic SP gamma ray log profiles and see how their environmental interpretation depends on the presence or absence of glauconite, shell debris, carbonaceous detritus, and mica.
A back-and-forth nervous SP gamma ray profile is typically of deep-water turbidite sands that could contain some or all of the 4 constituents of glauconite, shell debris, carbonaceous detritus, and mica. If the interval contained only glauconite and or shell debris, it would indicate winnowing, and the profile might represent the flank of a barrier island or marine bar. Or if it contained only carbonaceous matter and or mica, it would suggest a non-marine origin, as a distal distributary mouth bar, or crevasse subdelta. A coarsening upward funnel-shaped profile indicates well-winnowed regressive barrier island or shelf bar settings, when the sand contains only glauconite and or shell debris. If such a sand contains only carbonaceous matter, it suggests deposition in the proximal portion of a deltaic distributary mouth bar. The third motif is a blocky, uniform grain size profile and abrupt upper and lower contacts. If the sand contained glauconite and or shell debris alone, it could be a tidal sand ridge. If a sand with a blocky profile contains mica and or carbonaceous matter and no glauconite or shell debris, it is most likely a fluvial channel sand. However, if a blocky profiled sand contains glauconite and or shell debris together with mica and or carbonaceous matter, it is probably a channel sand from the proximal portion of a submarine fan. The last log profile shows a sand with an abrupt base and a fining upward transitional top. This type of profile indicates filling of a channel by lateral accretion. Such a sand body with mica and or carbonaceous detritus alone is non-marine and indicates a fluvial or delta distributary channel. The presence of shell debris, possibly with mica, and carbonaceous matter indicates a tidal channel sand. The presence of all three constituents, along with glauconate, suggests a submarine fan channel. As we've mentioned, another wireline logging tool useful in facies analysis is the dip meter. The dip angle and azimuth of dipping beds are computed and presented on one of several displays, the most common of these being the arrow plot, often called the tadpole plot. Dip is read by the position of the tadpole base on the dip scale, and the azimuth is read by the direction in which the tadpole tail points.
Traditional uses of the dip meter include the diagnosis of structural features, such as folds, faults, and unconformities. The dip meter can also be extremely valuable in facies analysis as an indicator of sedimentary structures. It has been found that dips arrange themselves into characteristic patterns on tadpole plots.
Slope patterns are characterized by upward decreasing dips of generally common direction, often called red dip patterns. When generated within a sandstone, they usually represent lateral accretion surfaces of a channel sandstone. Ideally, such dips should point in the direction of the stream axis and perpendicular to stream flow. Slope patterns may also be developed in fine-grained sediments where they represent drape or differential compaction over a more rigid underlying feature, such as a sandbar or reef. These dips point in a direction away from the crestal high of the underlying feature. Current patterns are upward increasing dips of common direction termed blue patterns. They are generated by the concave upward foresets of current-induced cross-stratification and naturally point in a down-current direction. Because of the limited thickness of many individual cross-strata sets, recognition by the dip meter requires use of computer programs that calculate dip in very small vertical intervals of a few inches. Upward increasing blue patterns are also produced by prograding deltas, barrier island sequences, and submarine fans. In these cases, dip generally increases upward along with increasing grain size, and a single pattern may extend over a large vertical interval. Any post-depositional structural tilting of strata is reflected in the generally low-angle parallel dips called green patterns that typically occur in shale. Such tilting can cause depositional patterns to be misinterpreted, and therefore structural dip must often be removed from dip meter presentations. Before we go on to the next section, let's look at some dip meter motifs along with corresponding SP gamma ray profiles of a few common reservoir sands. Here we see the diagnostic motif of an Aeolian sandstone, as displayed by the Permian-Rotliegend Formation of the southern North Sea. Blue current dips generated by coarsening upward toe-set beds pass into uniform high-angle foreset dips. Wind currents can clearly be seen to have varied in direction from southeast to northeast. This is a fining upward SP gamma ray profile of a Miocene distributary channel sand from the Louisiana subsurface. A distinctive pattern of red slope dips representing channel accretion surfaces is shown pointing toward the center of the channel and normal to the long axis of the channel. Logs of deep-sea sands from the North Sea show upward increasing blue patterns, opposite upward coarsening submarine fan lobes, and upward decreasing red patterns in the overlying middle fan channel sequences. The blue dips point in the direction of fan progradation, and the red dips point toward the center of the fan channel or normal to channel flow.
You will find log profiles and dip meter motifs of major reservoir sandstones in your manual, as well as in the appropriate modules of the GL 500 series. Because of the mostly in situ nature of their deposition and their high susceptibility to diagenesis, most carbonates do not show distinctive dip meter patterns. Now let's consider the second major indirect source of subsurface information, seismic surveys. The importance of this type of data has increased with the development of a branch of seismic interpretation known as seismic stratigraphy. Two fundamental procedures in seismic stratigraphy that relate to the analysis of sedimentary facies are seismic sequence analysis and seismic facies analysis.
Seismic sequences are the seismic expression of the depositional sequences we discussed earlier. They are packages of seismic reflections from sediments deposited within a specific time stratigraphic unit. The three-dimensional shape of seismic sequence units often provides an indication of depositional setting. An example is the distinctive mounded shape and downlap relationship of a submarine fan when viewed along a strike section. Seismic facies describes the configuration and character of seismic reflections resulting from the depositional environment. One type of internal configuration particularly useful in environmental reconstruction involves progradation and can be divided into two classes, oblique and sigmoid. Oblique progradational units are characterized by toplap, or angularity, at the upper boundary of the sequence. This type of configuration implies high-energy depositional conditions, for example, at the front of a prograding delta. Fairly clean sands can thus be anticipated at the top of oblique patterns. Sigmoid progradational units are distinguished by flattened S-shaped reflections, indicative of upbuilding as well as outbuilding of the sedimentary prism. In this situation, deposition usually takes place in quiet, deep water, and sediments are usually fine-grained. Reflection character is defined by the amplitude or strength and the continuity of reflections. It has been observed that high-amplitude reflections with good lateral continuity characterize sediments deposited in quiet water conditions, for example, interbedded marine limestones and shale. High-amplitude reflections with poor continuity imply continental deposition, for example, interbedded channel sands and shales. Low-amplitude reflectors with good continuity characterize deep-water shale sediments. However, acoustic contrast can be so low in deep-water shales that they can appear almost reflection-free. Hummocky reflections can be produced in high-energy, shallow water conditions, for example, shallow marine sand bodies. Facies analysis can be further aided by the use of special seismic techniques, such as 3D seismic and color displays. There can be no more direct indication of a depositional environment than presented by the meandering stream pattern on the 3D horizontal time slice seen here. Color displays of reflection amplitude and frequency can often reveal facies changes and environmental relationships that are not evident on conventional seismic sections.
Let's now briefly examine carbonate facies. Porosity development in carbonate rocks is much more variable and erratic than in terrigenous sandstones, and is often created by diagenetic processes. There's often a close connection between depositional environment and these subsequent diagenetic changes. Thus, explorationists have learned to focus their attention on depositional models and facies trends.
Because of the complex nature of carbonates, detailed examination of the rocks themselves is usually essential in environmental diagnosis. Hand specimens should be examined for color, sedimentary structures, and rock texture. Microscopic examination using thin sections if possible should include determination of any dolomite or evaporite, proportion of carbonate grains, grain size, and grain type. Common sedimentary grain types include ooids and skeletal grains that are usually found in shallow, high-energy settings, piezolyths and oncoliths, which form in lower-energy depositional settings, aggregates and lumps, which form in sandy shelf areas where wave energies are moderate to low, pellets that are winnowed out of high-energy settings and are often preserved in quieter water environments, and lithoclasts, which are rock fragments resulting from erosion of older carbonate rocks. These are often deposited as talus and breccia in deeper water at the base of carbonate slopes. The commonly accepted classification scheme for carbonate rocks was formulated by Dunham. It is based on textural features relating to original depositional fabric, basically the proportions of carbonate mud and sedimentary grains, as well as binding by in situ growth. Let's look at Dunham's classification in relation to depositional setting using the carbonate shelf model. Mudstone is composed of carbonate mud with less than 10% sedimentary grains. It is typically deposited in quiet water environments like tidal flat, shelf interior lagoon, and basinal settings. Waxstone has greater than 10% grains, but the grains are mud-supported. Waxstones are commonly found in shelf interior and in outer shelf or foreslope settings. Packstone contains some mud, but not enough to be mud-supported, and sediment grains thus support each other. Packstones occur on the immediate landward and seaward flanks of the shelf margin barrier setting. Grainstone has no mud content. The grains support each other. Well-sorted grainstones are deposited in shallow, agitated water environments, like carbonate beaches, shallow shelf areas, and on the shelf margin proper. Boundstone is bound together during deposition and occurs as ecologic patch reefs on the shelf, pinnacle reefs on the foreslope, and as ecologic barrier reefs on the shelf margin.
Now let's examine a special type of carbonate rock, dolomite. Dolomite is important because it is generally a more porous and permeable rock than limestone and forms many of the best carbonate oil and gas reservoirs.
Dolomite forms by the process of dolomitization, when calcium carbonate, such as aragonite or calcite, with the addition of magnesium, is replaced by calcium-magnesium carbonate. Fluid imports magnesium, dissolves the precursor calcium carbonate phase, precipitates dolomite, and exports calcium. Although some evidence for primary dolomite exists, many believe that modern dolomite is pentacontemporaneous, growing by replacement of aragonite or calcite in unindurated muddy sediments in restricted evaporitic tidal flat environments. This type of pentacontemporaneous dolomite is universally composed of small crystals, ranging in size from 2 to 4 microns. Because of its small grain size and susceptibility to cementation, it may not, by itself, form good oil and gas reservoirs, particularly if formed in the supratidal zone. However, it is an excellent indicator of tidal flat shelf interior environments. Dolomitization may also take place in other settings, such as the middle shelf and shelf margin, or in ancient lithified carbonates. In these cases, recrystallization of pre-existing limestone occurs, producing large dolomite crystals. Such dolomite does not, by itself, provide a reliable indicator of depositional environment. However, it can be an excellent reservoir rock.
This concludes our look at the basic concepts of subsurface facies analysis. There hasn't been time in this module for us to go into the facies characteristics of each important depositional environment. You'll find these covered in the appropriate module of this GL500 series. Before we close, let's quickly review the 5 basic parameters that define a sedimentary facies.
First, its lithology, particularly grain size, sorting, chemistry, and mineralogy. Then its sedimentary structures, its paleontology, primarily as revealed by its microfossil content, its geometry, and finally, its associated environments in both a lateral and vertical direction. We saw that these parameters may be obtained from direct sources, like outcrops, cores, and cuttings, or from indirect sources, such as wireline logs and seismic.
Remember that no single feature of any facies or subfacies can be considered diagnostic by itself. Most, in fact, can be found in several sedimentary environments. Therefore, where doubt exists, is it essential to keep in mind 2 or more facies while assembling and examining data. Good interpretation is a process that should mature as newer and hopefully more high-quality data are generated. Good luck.
This program has been sponsored in part by the following companies: ADNOC, ADGIP, Aramco, British Petroleum Company, Chevron Corporation, Mobil Oil Corporation, Petro-Canada, Phillips Petroleum Company, Schlumberger Limited, the Shell